Hello, good morning, good afternoon, good evening. It all depends on where you're watching this tutorial from. And once again, I want to thank you for being part of this community. Thank you for subscribing to my channel. Thank you for always coming back to be part of this community. And I promise to always keep bringing you tutorials on Aspen Hysys until you're fully you have a full grasp of how to use this all important simulation tool in the oil and gas industry. Alright, the last two videos was all about pipeline simulation, how to model pipelines in pipe segments, and how to predict pressure gradients across the pipeline. Alright, and today we'll be taking it a little bit further by using an Aspen Hysys V11 to analyze the flow assurance through the pipeline. Alright, before we continue, please don't forget, if you have not subscribed to my channel, please don't forget to subscribe to my channel, as more videos will be hitting your screen via this YouTube channel every single time. Okay, if you've not gone through our past tutorials, you can go through them, because most of the things I've done here were things I've taught in the past. Now what we have here is a mixer. This is a mixer which can be used to model a header, that's the manifold, and we'll have a pump. I've already taught on how to model a pump or simulate a pump and the mixer too. In our previous videos I've also taught on how to model pipeline. So today all we're going to be doing is just to analyze the flow assurance across the pipeline. So we have our hydrocarbon here, we have water, both of them commingling together to give us this stream. That's the hydrocarbon to pump. Now the pressure of this stream is 20 bar, and we're pumping it to about 100 bar. This is, like I told you in our past video, it's all about the arrival pressure, that's the pressure downstream. Okay, it all depends on where the stream is going to. If the facility needs a pressure between, let's say, between 90 to 100, okay, experience will tell you that you need to apply pressure to boost, or to apply pressure, bringing a pump, since it's a liquid hydrocarbon, bringing a pump to increase the pressure from 20 bar to around 100 bar, so that when you put into consideration the pressure gradient across the pipeline, the arrival pressure will be within the required pressure at the facility you're transporting the fluid to. Alright, so that being said, we are going to go straight to what we have for today. All I need to do now is to double click on the pipeline. It has already been modeled. Alright, in our last video I told us for us to check or predict the pressure gradient. All we need to do is click on performance and then go through view profile and all of that. Okay, that has been done. So today we'll just go straight to flow assurance. So when you click on flow assurance, you see CO2 corrosion, you see erosion, you see hydrate formation, slug analysis, wax deposition, as the case may be. And then for corrosion, before corrosion can happen within a pipeline, you need the presence of CO2 and water. And if you check the composition of this particular stream, let's do that. We'll go to composition, and you see we have 7% of water and 2% of CO2. So we need the presence of CO2 and the presence of water before you can talk about corrosion within a pipeline. So now let's see the effect of the CO2 and water in that line, or in the stream. Let's see the effect on the pipeline. So all I need to do, okay, before then we have corrosion model. We have about 3 of them in Hysys. We have the NOSOC standard, we have the WAD model, 1995 and 1991. I normally use the WAD model 1995. You can use anyone. Actually, the WAD model helps you with both the corrosion and the scaled corrosion, whereas the NOSOC just gives you the corrosion. So I normally work with the WAD. That doesn't mean that others are not reliable, okay? So I'll just select the WAD, and I'll click on do corrosion calculation. So once I click on this, it automatically generates the data. Okay, it will take into consideration everything, all the parameters I've imputed during my simulation, and then generate this result. Now let's look at the corrosion rate per year. Now if you look at this is the corrosion rate per year. This is scaled corrosion rate per year, which is the same actually. So what this means is this. You remember when you're modeling your pipeline, when you're running your pipeline simulation, you put into consideration corrosion allowance in most cases, which is usually between about 3 millimeter or thereabouts. So when you put everything together with the pipeline thickness and everything, you might have roughly 15, 16, 14, 16 or 18 millimeters. The case may be. It all depends on what is passing through the pipeline, whether gas or liquid. Alright, now let's assume the thickness of the pipeline. Let's assume the thickness of the pipeline is 15 millimeter, having put the corrosion allowance into consideration. Now what it means is this, that every single year you'll be losing about 4.60115 at the inlet of that pipeline every single year. So if we take this down, this is about 6,000 meter pipeline. Yeah, 6,000 meters, that's 6 kilometer pipeline. So what it means is this: when you divide 15 by 4, you have roughly 3 point something years. That means in approximately 4 years, your pipeline would have been gone. That's what it means. All right. So that is, Hysys helps you to predict this, and you already know what to do. You need to bring in corrosion inhibitor, or you might have to dehydrate the stream coming in. All right. Or probably you might have to try as much as possible to remove the CO2, okay, to develop a process to remove more of the CO2 or the water, or you can use corrosion inhibitor to solve this problem so as to preserve the pipeline within the design life span. Most of the design is approximately 25 years or so. So when you design your pipeline, it should last for about 25 years. So if you're putting that into consideration, your corrosion rate should not be up to 1 millimeter per year. No, it should not be up to 1 millimeter per year. It should be about 0.6, 0.5 or something like that. So whatever you're doing, your modeling should be within that range. Alright, so this is how to check out for the corrosion rates across your pipeline. Then the next thing we'll consider is the erosion velocity. Alright, before we go that, you can actually see the plot. That's the table for corrosion. So we'll go to the plot. Now from here you can see this is the scaled corrosion, this is the corrosion, everything on the same line. So you see the corrosion decreases, the corrosion rate decreases across the pipeline, across the length of the pipeline. So from this graph you can see that, okay, across each point of the pipeline the corrosion rate decreases. Right, that's what that. So we'll go straight to erosion velocity or erosion. Now we know that when the erosion velocity is extremely high, okay, it has the tendency of carrying the particles or the wall of the pipeline, taking the particles off the wall of the pipeline. Okay, why corrosion has to do with electrochemical reaction. What's it called? Erosion has to do with mechanical eroding of the pipeline. So it has to do with movement of the particles of the wall of the pipeline, all right, due to high erosion velocity. Now, on the other hand, if the erosion velocity is very low, if it is very, very low, it's also not good because it can lead to the deposition of debris within the pipeline, thereby reducing flow. Okay, so that's on the other hand. So these are the things you have to consider. So what we need to do now is to click on do erosion calculation. So we'll do this from the table. You can see this is the fluid velocity is this, the erosion velocity is this. So our erosion velocity is near 0 if I'm not mistaken. So we'll go straight to the table. From here you can see the erosion velocity is 0. The bulk velocity is 8 point. So we won't have erosion for this particular simulation, this particular model. We won't have erosion within the pipeline, but there's also a risk of debris coming in with the hydrocarbon being settling inside the pipeline. All right. By standard, the erosion velocity should be approximately 3 feet per second. All right. So that's for that. So this will really help you too. Then the next thing you can check is the hydrate formation. What leads to hydrate formation? More of water in the stream passing through the pipeline. So let's check this. All I need to do now is click on do hydrate profile calculation. So once I do this, we'll have different types of hydrates. Sorry, my system is active. Sorry about that. Alright, sorry. Okay, so for the erosion, we have different model. We have the NG Robinson and we have the CSM. So all I need to do is click on the do hydrate profile calculation and it automatically will run the calculation. So let's look at the table first and we'll be able to interpret the graph properly. Now, this is telling you, if you look at this, we have the distance, we have the pressure, we have the temperature, we have formation. This will tell you whether hydrate will form or not. So based on the quantity of water we have in that stream, this is telling you that hydrate will not form. Alright, but it's telling you hydrate, the type of hydrate that will form. Okay, this is telling you that if hydrate will form, the first thing that will form will be ice. Alright, so that is that. If you go to the plots, you can see the temperature and the pipeline what's called plots. All right. Now, if you look at these are the different types of hydrates. So for this particular simulation, hydrate won't form. All right. But if hydrate will form, you will see one thing you will see is this. You will see the type of hydrate. For instance, since from the table, you remember, let's go back to the table. I want to show you something. For this table, you will see the type of hydrate that will form if hydrates will form. Okay. Now it's telling that ice will form first. So if we go back to the table, this is what you will see. Now let's look at these indicators. All right. So from this, you see this is ice. Ice forms first. So this is telling you that the ice will form across the length of the pipeline. That if hydrate will form. Alright, but based on the condition of this pipeline, the temperature and the pressure, the operating pressure and the temperature rather of this pipeline, we are not expecting hydrate to form within this particular pipeline. Alright, so that's for hydrate formation. Now if you go to slug analysis, if you have slug, alright, it will generate that, but unfortunately we don't have slug in the pipeline. So from here you can get your liquid density across the pipeline, you have the liquid viscosity across the pipeline, and the same thing with wax deposition. Unfortunately we don't have wax. This is because of our composition or the composition of the inlet stream. Okay, so I guess this will help you a lot. And next time you want to model a pipeline or check out for flow assurance of a pipeline. Alright, thank you very much for your time. I really appreciate the fact that you always come back to this channel. Okay, really appreciate it. Thank you once again. Okay, look out for my next video. Don't forget to subscribe to my channel, as more video tutorials will be coming up shortly. Thank you, and you have a wonderful day ahead.